I'm MC Brown. Everybody hopefully knows me by now. You all saw me on the keynote. You saw me on the panel. Yeah, no, you've already got it. You've already got it. Yep. You're welcome. So, what I want to talk about today is heterogeneous replication. And what I want to talk about actually partially is just general heterogeneous replication. Right, okay, and I want to talk then specifically about what we do in the replicator, and I'm going to describe into a bit more detail about how we do it in the replicator and how we make that practical. Then I want to tell you about what we're actually doing in the replicator and adding further down the line. I'm going to show you how it works. I'm going to show you how we do things. I'm going to show you some of the considerations that we have to take into account when doing heterogeneous replication, because believe me right now, right, heterogeneous replication is not as straightforward as it sounds. Right, so the first thing I wanted to do is I wanted to make everybody aware of a few things, right? Heterogeneous replication is never exporting and importing data, right? It is never doing ETLs, it is never doing one-time exports, it is never migrating your database to somewhere else. Heterogeneous replication is about permanent, live, constant, low latency transfer of information from one database to another. If it is not that very first line in that, it is not replication of heterogeneous data. Okay, because outside of that, you're not really replicating data between two systems. You stick it on a message bus, you don't have any guarantees, maybe when it gets there, you don't have any idea that it's actually made it. You should make sure that you're always doing it by transaction, you're always getting the information across. But actually, more importantly, there are a whole bunch of other considerations, right? And one of them is you've got to make sure that the data is in the right format, you've got to make sure that information is exchanged in the correct way. So the first thing is I want to be very, very clear that you need to know that not all databases are created equal. Now, how many people in here, all three of you, how many people in here are using multiple databases in their environment? So that is more than just MySQL or more than just, I know you're using, you want Cassandra, so I know you're down the line you're doing it. Yeah. So you got Redis, did you say? Yeah. Okay. Okay. All right. Yeah. So one of the big problems, right, is there is a big difference about migrating data between transactional and non-transactional systems. Right, okay, transactional database systems work in a very specific way, and hopefully we're all familiar with that, right? We know when a transaction has been committed, we know when the data has been written down, and we can guarantee it's reached over the other side. Non-transactional databases don't have that. And there are non-transactional databases out there, and non-transactional methods of distributing and storing information where we have no idea whether something has reached its destination. So later in this presentation, I'm going to talk about Kafka. Kafka is actually a very good example of that. You put something onto Kafka, you put it onto a message bus, and you hope to God that something that is subscribed to your Kafka topic is going to pick it up. But you have no guarantee of that, and your replicator doesn't know that it's actually done that. All we've done is we've pushed the data out and hoped to God it's reached its other end. The other thing is actually there's a huge bunch of information in terms of all of the different objects, right? Every single database has its own style of referencing to different objects. Even between MySQL and Oracle, for example, Oracle refers to schemas rather than necessarily databases. MySQL calls it a database. Oracle then has a very, very weird way of looking at things, which is that actually doing stuff across multiple schemas is not something that Oracle likes to support, something that actually MySQL does as standard. It's very easy to say, insert into something where something else across multiple databases in MySQL, and we don't give it a second's thought. And as we dig down into this stuff, right, there's a whole bunch of stuff, right? What's a record? What's a field? What's a column? Is it a collection of related tables? What happens if we happen to be specifically replicating data and we're only replicating a subset, and they happen to be ones that all have references to foreign rows, and they're all foreign keys? Do we consider that to be a database? You know, what happens if we happen to be replicating into a document store? If we were replicating into MongoDB, which Tungsten Replicator does, what are we actually really replicating? Are we only replicating the table data into something that looks like a document because that happens to be convenient? Or should we maybe be combining multiple tables together because that would normally be what you would do in a document database? Right? If you ever model an application for a relational database over a document database, you might have 20 tables in your relational, but you might have one document. Right? How do you handle that? How do you treat that? How do you understand what all of those different things look like? And what do we treat ultimately as a row? Right? We're all familiar in a typical MySQL transactional database, Oracle, a row we consider to be a record of information. But actually in another database, it could be something totally different. If you look at something like Vertica, Vertica is a column store. And although it has rows of data, we're actually more interested in the columns than we are in the rows. So what's actually a row of information? So that leads us to getting awful diagrams like this, right, where we try and understand and map between all of these different formats and all of these different systems. So this is actually part of a project I did when I was at Couchbase. We were trying to teach people how to migrate their databases from MySQL into Couchbase. Couchbase is a document store, main competitor to MongoDB. We had to teach people completely how to rewrite and rethink about their database structure and understand how that was going to work. Then, of course, we have to start looking at and making some comparisons, right, about what can we actually do. What is translatable from one place to another, right? So let's have a look at something very, very simple. If we have a look at MySQL to Oracle sounds like the easiest thing in the world to be able to replicate. They're both row-based databases. They both support SQL. They have very, very similar structures. I can create tables. They've all got different fields. Any idea what the biggest headache for MySQL, actually MySQL generally, but MySQL to Oracle is? Anybody want to offer that? Enums, sets, these don't exist in Oracle, right? If you want to insert information and you happen to have used an enum or a set, don't exist in Oracle. You have to convert it into something else. So we've now gone from this position where we have a nice single number that represents an enumerated item. And when we replicate it over, we have to convert it to a string. Right? We have a filter for that in the replicator that actually literally converts it into a string. So now we've got a different problem. Now our table definitions don't match. I cannot take the DDL of a create table definition from MySQL and put it straight over to Oracle. And I can't do that because now there isn't an enum and I have to create it and say it's a string, but I've got to work out how long the string is by working out what the size of the longest enum object is. Right? Yeah. So now we've completely made a different change. It gets worse as you go through, completely different database systems, right? Okay, so if you're going from an RDBMS, so let's say you're going from Oracle and you're going to a completely free text, unstructured data, and let's say we wanted to dump out information into something like Hadoop, and we're not doing it into something that looks like rows. We're very, very deliberately maybe only taking a single record or a single field from a table within MySQL and putting it over the other side. How the hell do we work out what that's supposed to be? Should that all be dumped out as one great big file that we've munged together, or should we output that as an individual file for each record, or what do we do? It then becomes application specific, because at the other end, we've got to work out how we access that information out of the Hadoop system in order to make it usable. Then there are some other things, right? We have to understand our data. I cannot tell you enough, right? So in Tungsten Replicator, we actually have a tool called DDL Scan. And with DDL Scan, what we do with DDL Scan is we try and map one data to another data type. And it does that by a very, very simple template mechanism. And it says if it's an int on this side, then we convert it into an int on that side, right? If it's, yeah. No. So it actually looks at the DDL of the source table. So to me, that's a relatively inefficient way of doing it. And the problem with DDL Scan is it's a one-shot item. And by that, I mean there's no functionality within DDL Scan that if you change the table later, we can create an alter table statement for you. It's literally, we can take one DDL structure and convert it to something else. Change it after that, it's your problem. But it's also very limited, and it's also very limited because you know, we move that data across, and all we can do is say int to int, right? All we can do is say, okay, so ints aren't supported on here, so it goes int to big int. You know, if it's a tiny int on MySQL, so again, Vertica, good example. Vertica doesn't have a tiny int. Vertica doesn't have a Boolean either, right? So you know, you end up having to do these determinations, and then there are other things as well. You know, another thing. Really, you know, Vertica has a maximum size of varchars, or it used to actually. They've upped it recently. Varchars was 4,000 characters. So what do you do if you've got information larger than that? Do we just truncate it? You know, how do you handle that level of information? Verticas are updated. That was Vertica 6. It's updated a bit differently. But this introduces all of these other problems, right? If you're replicating the data, we want to be doing it effectively. We want to be doing it in a way that we do not lose or remove information. If you want to filter out fields, you want to filter out tables, you want to select something that you want to pull out each time, that is absolutely fine, right? I have no problem if that's what you want to do. But bear in mind that you start to get to the point of the replication. My principle always with replication is if I've replicated it from one database to another, so if I've replicated it from, say, MySQL to Vertica, I should be able to take the stuff I've replicated in Vertica and migrate it back to MySQL. Can't replicate it because Vertica doesn't have anything useful for changelog. But I should be able to do a dump out of Vertica and put that back into MySQL without losing the data. Without losing the precision, without losing the length, without losing anything. Otherwise, we're not replicating the data. We are replicating a subset of the information. And then it becomes really nothing more than an export and an import, just a little bit faster. It has to be low latency. And I stress this again and again and again, right? Everybody can do an export and a dump. Anybody can do a load. Anybody can sit there and work it out. I'll give you an example. So we used to do replication for Booking.com for everything out of their MySQL databases to put it into Hadoop. And for Booking.com, everything out of MySQL into Hadoop, what they used to do is they used to use a tool called Scoop. And Scoop basically does a select star on table and dumps all of the information out into a CSV file over on the Hadoop side. They did that across 30 servers. It took them 7 hours. They did it every single night. And it maxed out their network utilization for that 7 hours, right? 100% network utilization for 7 hours while they dumped out that information. We came in with a replicator, and we started replicating live information, so they no longer needed to do a full table dump anymore. Their latency of getting that information went down from 24 hours to less than a minute, and their network utilization went to less than 5%. That's replication, right? Right there, that is the definition of replication. The last item is something that actually, to be fair, with Tungsten Replicator, we're still working on. And that is automatic mapping. And that kind of goes back to my comment about DDL scan. Right? DDL scan is a one-shot item, and that's fine. But actually what you want to do is you want to be able to make something that's automatic. So if I create a new table over on the MySQL side, it automatically gets generated over on the target side, and I never have to consider about the fact of what's happened. And I also want to be able to cope with changes, right? I want to be able to cope with the fact that if I add another column over on the other side, we ultimately go ahead and add that column onto the target database as well in a sensible way. And I think I've got a slide that will cover that in a bit more detail because we are adding something in an upcoming release that will solve those problems for you. Obviously, data typing, indexing, right? Last item, often something that's forgotten. There is no point in us moving the data across over to the other side if we don't also map across the indexing, right? Because if the data is not usable when it reaches the target, then what was the point in replicating the data? Okay, we've got to replicate it across, and we've got to be able to reproduce something that enables us to get it back out as efficiently as we were originally using it on the MySQL side. So in Vertica, that means we've got to have order clauses, which is how Vertica does. indexes. We've got to be able to identify and say this is an important column or this isn't an important column. Maybe when we're replicating it into a document database, we make sure that we create whatever required index is over on the other side. So we can do that in MongoDB. We can create a suitable index. We can make sure that we create a necessary index on that side. That's not something we do yet, but it should be in the new version. When we do Couchbase, and we will be doing Couchbase, we want to be able to create a suitable MapReduce index that creates the correct information that matches the one over the source side. Every single time, right? It's got to work. If I replicate my data, I've got to be able to use it over the other side, and that means replicating everything. Not just the data structure, the data types, the indexes, the whole works. So, I've kind of covered some of this already, but I'm going to dig a little bit deeper because I can't tell you how stupidly frustrating this particular system is. So data types are not supported everywhere. For some, the type doesn't matter. If we're replicating into Hadoop, for example, we replicate data into Hadoop, we put it into HDFS, it appears there as CSV. If you happen to be using Hive, the way Hive works is Hive looks at the CSV, and every time it reads every single row of data out of the CSV, it applies its DDL to the output. So if you happen to have specified DDL and said this is a date, Hive will go in and try and pass that particular column from that particular row into a date and display it. It's not stored as a date, it's a CSV, right? So you have to be really careful. For some customers, and some people just generally, when they move data across over into Hadoop, what they do is they don't bother with any type whatsoever. Just everything is a string. I'll worry about converting it into a type once I've resolved the data. Because it doesn't actually make any difference to Hive. The only time it makes any difference is if you do like a sum on a column or something, it likes to know that it's dealing with all ints. But then you introduce the problem that it has to do that every single row. It's not stored as that format every single time. Remember other things as well, right? The format, the precision, the structure might be different. So different systems support different precision levels. For example, we can have a float and a double within MySQL. We can have a double within Oracle, but the size of the double is different. And the precision is different. Other things that cause problems, decimal as a data type. Over onto the other side, sometimes causes problems. Ints cause problems. Sometimes we have databases that don't support 64-bit ints. You're going to have a problem. And then there are some really, really fun ones. Those are numbers. They seem mildly fine by comparison. Dates is a problem. Some databases don't even know what a date is, right? Your only choice when storing a date is to convert it into an epoch and hope for the best, right? Even if they do support dates, they often support dates in different formats. What do you do about the fact that your source date might actually have been stored in a database that happened to be very US-centric? And believe me, there are some. So all of your dates are month, day, year. When you translate it over into the other side, you're putting it into a system where everything is Europe-centric. So it's day, month, year. What do you do about translating that? What do you do about the fact that some of them don't store time zone information? Some of them don't support seconds. Some of them don't support sub-seconds. Right? Strings. Not everybody uses UTF-8. What do you do if you're not using UTF-8? Or what do you do if you're writing from one system which isn't UTF-8 and you're writing into one that is? Usually you're okay. What if you're writing from something that is UTF-8 to something that isn't? You could be screwed. Because when the data gets over there in the other side, you're never going to be able to use it. Compound data types, I've already mentioned, enum, set, all cause all sorts of problems. And what about other things like binary types? If you're storing binary information and you've encoded it, how do you get over to the other side? So in MySQL, for example, we can store stuff in binary. You cannot write binary material out as CSV. Right? It has to be encoded in some format before it goes into CSV. So this is probably one of the bigger things, and it's going to sound like an odd thing to suggest. But extraction and apply rates are always different, right? And I'm going to give you some very, very good examples. We're going to have a look in more detail in Kafka later, right? But data extraction rates vary and data apply rates vary. right? So what if you have a system, and I'm not talking about, I don't care what system is underneath or how fast the system it's on or anything else. There are just systems that cannot cope with large ingestion of data. If you're looking at a relatively small database, you know, say you're running MongoDB on a small system and it's not clustered or anything else, and you're writing that data across, you could potentially have a problem, right? We could be extracting 100,000 rows, you know, every minute from MySQL, but somehow we've got to write 100,000 rows into Mongo over the other side. That can present a problem. How do you cope with that? But, and here's a very, 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 very different system, and I've just noticed a typo in the slide. So here's a very, very different problem. What do you do about the fact that we could have 1 million records in a single transaction on one side? The other side doesn't support transactions. So what do I do now? You could chunk it, okay. However, what happens if I have to stop in the middle of that? What happens if the target system dies in the middle of that process? If the system comes back up again, I haven't committed a transaction, I've only committed a part of a transaction. Do I reapply all of the ones from the start of the transaction again? If you've committed, you've got 1 million and you've applied 999,999 over into the other side and then it dies, when I start it up again, I've got to now apply the full million, right? We're trying to remain transactionally consistent. We're trying to apply data in a way that we know it's reached the other side and we can say, yes, it's there. How do we cope with that, right? How do we do about things like other things? Obviously, the reverse is opposite. So you were in my session on Tuesday, right, where we're talking about batch loading. Writing data into Vertica is much quicker if I could do it 100,000 rows or 200 or 300,000 rows at a time, right? We want to be able to batch apply. In the big scheme of things, that way round is easier than the opposite, because actually collecting multiple transactions together and committing them as one transaction is much easier than committing one large transaction that we ultimately have to do as multiple small ones over the other side. We can always expand, we can't contract. Smallest level of detail should be that transaction. Obviously, you also have problems if we do bulk extraction. So we do things like with Oracle, we have something called the parallel extractor. The parallel extractor will pull out as many rows as possible from the data and then try and apply it down. And it feeds that through the replicator so that they're available as a transaction. You get that same problem that I just described. You could have one massive transaction with 1 million rows that we've now got to try and apply down over to the other side. Ultimately, all of this stuff has got to be non-destructive, right? Otherwise, if it's destructive in any way, it's not replication. So, what's the solution? You can probably see where I'm headed with this, but, you know, okay, so what's the solution? Right, so we need a native neutral format. We need a way of storing data in such a way that we can extract it from anywhere and store it, and then also, having stored it, apply it to any target system. And it's got to be completely and utterly neutral, right? If it's not neutral, none of this stuff is going to work. We also have to have the ability to change that data as it goes through, because as we apply it down to different systems, we've got to be able to make a determination that says, okay, I need to write this in as a different format. So we have something called a zero dates to null filter. Zero dates in MySQL, I don't know whether you're aware, you can insert a zero date. You know, 000000 times 0000. Perfectly valid in MySQL. MySQL is the only database in the world that supports that. Right? Most other databases would have null. Right? You can't have 0 day of 0 month of 0 year because no such thing exists. It kind of does, but you know what I mean. Right, on a practical level, it's unlikely anybody would ever want to store it. Sorry? Well, yeah. Yeah. Yeah, that's a whole other world of hurt going that direction, but yeah. So that's why we convert it to null. We convert it to null so that we can write it into Oracle, and Oracle won't complain about it. I would argue on some level that's loss of information. unless we make the rule that we know that a null date on an Oracle system, we would create a null date to 0 for doing the opposite way, right? If you know that that's what you've done, you could know how to convert it back. We're not really destroying the information, we're just storing it in a way that is supported by the target system in that case. There are other examples, right? We want to be able to maybe remove columns, we maybe want to be able to munge columns together, we want to be able to maybe truncate text, we may want to be able to truncate the size. That breaks that rule, right, of not being destructive, but if it enables it to get you the data into the other side, that might be what you have to do. And again, we have filters that would support that. You might want to do really, really weird things, and I mentioned some of these on Tuesday, right? You know, deserializing Perl structures into JSON, just so that it could be written into the other side and understood by the Hadoop system, right? If that's what you've got to do, that's what you've got to do to make it usable. It's non-destructive, all we're doing is changing the format of the embedded information. Why you would store a serialized Perl object in the first place, it escapes me. Says the guy who's done it, but, you know. We got it. The other thing, we need something that's standalone in nature, and standalone in nature, by that I mean it needs to be something that is independent. And the reason it needs to be independent is I need to be able to extract into that standardized format without having to worry about the other side. I should let the other side worry about converting from the standardized format into its target. Right? And there are multiple reasons for that. One is that's non-destructive. If I don't actually make the changes until the point where I apply it into the database, the storage of that interstitial format is never going to change. And if I suddenly decide I'm not going to write into MongoDB, I'm going to write into Cassandra, I can still read from that information and ultimately make the change at the last step. Obviously, it should be two-way. In an ideal world, we would be able to migrate data from one system to another. Obviously, that's very, very difficult. There are some systems that just do not have a method for getting your data out for the purposes of extraction or replication. So MongoDB is an example where there is actually a changes feed in MongoDB, which we can sit and read off. Couchbase similarly has a changes feed, as does CouchDB. Things like Cassandra sort of does. Redis sort of does. There are different tools. It depends on whether they happen to be generally clustered in nature, or whether they are replication aware by their own admission. But not all systems are like that. But the point is valid. We should be able to support from anything to anything while still going through that neutral format in the middle. And we should be able to handle the impedance problem, right? Whether it's batching up or whether it's chunking down. I should mention, by the way, by default, we actually already chunk within the replicator. And so if you're applying lots of rows into MySQL, we've discovered that applying a huge volume of stuff into MySQL as one big chunk causes MySQL to slow down. And so we actually automatically chunk it for you into a suitable size so that we get the data across in a suitable fashion. In actual fact, we can do like 5 transactions of 200 rows and you get 1,000 rows in, and it takes less time than trying to get 1,000 rows in. No, we don't understand why that is either, but, you know, I did wonder for a while whether it was to do with indexes, but actually sometimes what we do is even if you switch off the index or even don't have an index, the same is true. But for why there's that slowdown, I don't know. I haven't gone in and looked at MySQL. There's probably something in there. So guess what? Tungsten Replicator does most of this. In fact, it does all of this for the types that we support and the databases that we support right now. Right? High performance, flexible storage, interchange format, that THL is really, really critical. Built-in filtering, operates standalone, stop and restart. Right? Not a requirement I've mentioned up until now, but I must be able to stop the replicator at some point and stop it applying in or extracting out, and then restart it without having to start all over again. Right? If you can't stop and restart, then you're always going to be ultimately synchronizing the entire database. Right? There's no point in synchronizing the entire database. I've got a terabyte of information over here. Each time something happens and I have to restart, whether it's a network break or the target system dies or whatever, I don't want to have to start all over again. Okay? Start and stop is critical. And that's both sides. Right? Finally, transactionally consistent. As far as I'm concerned, It doesn't matter if your database doesn't support transactions. At the end of the day, I want to be only applying full transactions and extracting full transactions at any one time. There is no point in doing anything else, right? They're a nice, understandable block, and it doesn't matter whether you have auto-commit turned on MySQL, and so we always know what a transaction is, or whether it's handled some other way and you've got big transactions, like, say, from a MySQL dump. You know, we want to be able to have that transaction, because that transactional consistency gives us a natural break in the data to be able to say, I can stop here. I can do something here. Maybe this is the point at which I batch it up. Maybe this is the point at which I chunk it out. But ultimately, I say at the end of this, I know I've transferred that. Right? We need that break. There needs to be something that says, because otherwise we don't know it. We don't know the data. We don't know the database. We can't tell you how many rows, how many tables or something has been changed outside of that transactional notation. Finally, Tungsten Replicator, open source. Just throwing that out there. So applying data. So, you know, if you were in my talk on Tuesday, we had a look at how we're applying data. I'm actually going to specifically look at Cassandra, which is what I was going to do even before this gentleman here said he was interested in doing Cassandra as a target system. And I am going to try and show you how that would work, and it will be in a future version. But basically, there are going to be two methods for applying the data over the other side, right? Natively, we can just apply it down through JDBC. If your target system supports JDBC, at the bottom line, all we have to do is construct a JDBC statement, right? The incoming data is going to be in rows, because heterogeneous can't do anything but operate on a row basis, because we're not going to start translating SQL. And in case I don't need to point it out, MongoDB doesn't support SQL. So the only way for us to get the data out of something like MongoDB would be as the equivalent of row-based data, right? But we can construct it. It's very, very easy to construct something that looks like insert into something values, you know, based on the incoming row data, and we know the structure. JDBC applier, there is a slight niggle in that we need to be able to record our data position, which requires adding a data source specification to our system. But in theory, we can actually apply to anything that supports JDBC. And indeed we do. Batch applier, so I went through the batch applier in more detail. We're going to have another look at it today. Batch applier is great because obviously it enables us to do it in bigger blocks, but is very, very flexible in that it also enables us to apply into different target systems that maybe we wouldn't have been able to do before. So batch apply, quickly going to go over this. Way batch applier works, we dump out information into CSV, and then we use a JavaScript process which sits there and loads that CSV information into a staging table within the target database. And then from that staging table, we then merge that data into what we call base tables, which is basically the carbon copy of the target. And we can apply this to any system, even if it's not necessarily looks like tables. The same basic principle is there. Generally, the reason why we do it in a batch applier is because at the moment most of our targets are out into big data, and so it's much more efficient to load that data out. I will quote the same one as I did on Tuesday, right? I can, on my laptop, apply 300,000 rows every second into Vertica using our batch applier, right? That is staggering performance for that quantity of data. And it's very, very simple. When you consider in the background what it's doing is generating a CSV, copying it into a staging table, doing the merge where we say delete everything that's a delete and insert everything that's an insert using the last sequence number as the canonical version of the last version of the item. My God, 300,000 rows is good. I should point out, by the way, that's a single core CPU too. I've never tried it on multiple cores. I load a lot of data into systems, but if it can do 300,000 rows a second, that's fine by me. So what's actually really going on? Well, underneath within the batch applier, right, we generate a CSV file one table at a time, right? So one target table structure at a time, or one block of records at a time. And I say that very specifically. And then the function within JavaScript works by basically we have 5 functions. We have a prepare function. This kind of prepares the system for before we go online. So maybe what would happen is, this is not the part that would connect to the target database. That connection is already open, because that's built into the replicator already. But this is the bit that would maybe say, let's set some parameters to make it more efficient to import loads. Maybe I set the directory location. Maybe I, as we do in Oracle, maybe I set the the character set encoding so that I put it in. I set the default date format in Oracle, which is another thing that we have to set when we first go online. That's what that happens within the prayer. So every time you online the replicator, whether it's from startup or it's been offline, we run that little block. Then we have the begin. This is the start of the transaction. This is literally the equivalent of the begin statement in MySQL to say start of a transaction. And again, depending on your target system, we can do a whole variety of things here. What I tend to do when I'm writing out to a new target system is the begin is usually the point at which I empty the staging table from the previous load. Because at this point, in theory, it should have all gone in. But I leave it in there in case there's ever a problem and I need to debug it. But if I do it in the debug statement, all I got to do is just delete everything from that content. Then apply. Apply is the bit that actually does the process. Yeah. So just checking I have got that next item. So apply is where we actually do the process. So apply is where we actually do the copy the input into CSV into the table. And again, you can do this in any format you want. You have access to a JDB system. You are able to extract that data. You are able to make that determination of how we actually load that data into the system. Commit is the point at which we go end of this transaction or end of this block of transactions. This is what you do when you finish it. So this is generally when you would do, maybe this is the point at which you would do the merging and say insert everything and delete everything. Because actually this is kind of the final point where we say, okay, everything now into the table is done and dusted. And then obviously release. Release is when we go offline. Again, it's one of those things that's a bit like the prepare. You know, maybe we've got to do some cleanup. Maybe we want to clear up some temporary structures. We want to empty directories, whatever. We can all do it. Within this batch environment, we can do anything, by the way. We've got access to the target database. We can call out to the operating system and run commands. We can run other scripts. You know, we can do anything you can do within JavaScript. I mean, you can sit in here in JavaScript, and indeed we do. You know, I do things so the functions get down a copy of all of the information generated by the replicator when we generate the CSV. So where the CSV file is located, what the list of columns are, what the table name is, what the database name is, what the list of primary keys are. I go in some of our batch appliers, and I basically then escape all of those table names so that when we run a command, it doesn't matter if one of the columns has the same name as a reserved word within the target database because it's now escaped properly as it should be. Right? All of those things are accessible to you within this phase. And then during the transaction itself, we have to go in and do the actual process. Now, this process itself is going to be entirely dependent on how you're using the data and how you're operating. But I mentioned it before, the basic process is let's import the data from the CSV into our staging table, access all of that column and key information so we know we're updating, and then merge the data. Delete everything that's marked to delete, insert everything that's marked as the latest insert. Obviously, if you've uploaded the data and you specified the format, we can specify the format as being updates, so you could go in and update the information. There are also other things that you can do. So in our Redshift applier, and indeed for one of our customers who are replicating data into operative, what we actually do is we copy all of the staging information and we put it into a long-term table. And that long-term table contains a list of all of the changes to the database forever. And you can actually deliberately keep that information. So if you ever wanted to go back and do that time series stuff I was talking about on Tuesday, you can go in and do that. Now, obviously, at the end of that process, it's done. Now, obviously, different systems will work differently. If what you wanted was specifically to track the change data, you wouldn't have to do the merging. If what you were writing into was a system that didn't necessarily support the delete and insert, and you were able to do updates, so actually you could maybe do the MongoDB thing here. You could reformat the data into something that looked like a BSON record, which is JSON, within MongoDB. and then translate that and update each of the individual items. And if it was an insert, you just create a new item. If it was an update, you'd update it using the primary key information. That could all still be done within this process, within the batch applier. So let's have a look at actually what we do here. So the Cassandra applier is going into the next version, so 5.2 of the replicator, which will be out at the end of June. If I can do it, there may be a beta version in our 5.1.1 release, which will come out in 2 weeks' time. So you will be able to try this out. And basically, no surprises here. What we do is we go in and we copy all of the details. So Cassandra has a command called copy, which will load information from a CSV using a file name, but we have to specify the list of columns in our Cassandra table. And then what we have to do is we actually, within the JavaScript, what we do is we actually construct a list of all of the IDs that need to be deleted. So within the JavaScript, and in fact, this isn't done in the JavaScript, it's actually done in a little bit of Ruby code on the outside. Within the Ruby code, what it does is it looks at every ID within the CSV file that is marked as delete, and then configures it to delete that row within Cassandra. So we basically do delete from Cassandra table where ID is in this list of IDs. This turns out to be one of the more efficient ways of deleting a bunch of big records within Cassandra. And then when we do the insert, basically what we do is we insert into the sample using the latest version. And what the Ruby code does is it's gone through and it's picked out the last item based on the sequence number for each individual insert. And then we insert that into Cassandra as one great big huge block, you know, like we would with a multi-row insert statement in MySQL. And again, this turns out to be the most efficient way of doing it. I have not done any heavy testing on this, I will admit, for a while. But I was getting loading speeds of certainly upwards of 10,000 records a second loading into Cassandra with this method. And this was first version, you know, no optimization. I just wanted to see if I could do it. The entire process for doing Cassandra, it took me 3 hours just to come up with a new structure, a new batch file, and the Ruby to go in and do the processing and process that information. There's a bunch of other stuff that I didn't do from that, so I actually hand-coded the target Cassandra table, so I haven't done anything with DDL scan. But, you know, that's a minor thing in the bigger scheme of what needs to be done. So, all of that in mind, batch loading, that kind of formatting, that kind of processing of the information, getting that data in. This is how we will be adding support for a number of items. We are adding Kafka. Last couple of slides will tell you what we're actually adding into the replicator this year, and what we're trying to add in as both sources and targets. With Kafka, of course, we will use effectively the native method. It won't be native JDBC, but it will be native in the same way as our native Mongo applier is, right? We just use the Mongo API to be able to insert that information natively. We don't use the batch applier for that. The native applier is actually much, much quicker. And again, I haven't done heavy testing on that, but I think I have certainly done 20 to 30,000 BSON records a second into MongoDB with that method. That's a single MongoDB instance. That's not clustered. So bearing all of that in mind, right, actually getting the data over into the target system is only part of it. When we were looking earlier about data format, I want to make sure everybody is aware there are filters built into the system of the replicator, and the filters operate in a number of different places. And the filters actually work in a very, very, very similar way to the JavaScript loader that I just showed you. So, you know, filter operation, we always get one transaction at a time. At the end of that, at the end of the filter operation, we basically return that transaction. And it doesn't matter what you've done in that. At the end of the day, that filter has to return the transaction to the system. Must be processed in line. You don't have access to the transaction that came before or the transaction that comes after. You get one transaction at a time. And then it's a really, really complicated structure. This is the data structure for what information looks like in a transaction. It's really, really ugly, and I'm sorry, and I'm trying to build code that will make this a bit easier to use. It's awful. It's actually slightly worse than it looks here, because one row change, which is the lowest item here, so this is row-based data, one row change actually contains a list of all of the columns of the data, and in order to change something, I have to go in and search to the column in question and change it. I can't just say change this column to X. And I can't say change this column to X on every row. I have to iterate over each row and iterate to each column in order to choose which item to do. It's a nightmare. Anyway, we always return the transaction, always going to be SQL or row information, right? If you're doing MySQL to MySQL, obviously we will translate SQL statements for you and you don't have to do it. You can still do changes on SQL statements, although it gets much harder. But the same process is true. Actually, JavaScript filters, most filters are written in Java, but you can write your own JavaScript filters. And JavaScript filters basically have three. You have a prepare, what happens when you go online. Maybe you load a configuration file. You have filter, which does the work. You have release, which happens when it goes offline. You have full access to the connection to the database. You have full access to the Java class environment. Any Java class you want to load at this point, you can get access to. And we've now added in 5.1 that came out this week, we've added a bunch of utility functions into this area so that you can go ahead and do a bunch of items as well. So if you want to output something and change it into JSON, you can now do that inline. Strangely enough, our JavaScript environment is based on Rhino, and Rhino does not support the ability to convert a JavaScript object into JSON. Don't ask me why, it seemed like an obvious thing. So you have to write it in JavaScript. Beauty of JavaScript, of course, is that in JavaScript you can write your own function like that. So here's an example of actually how we would get an individual value, and I told you it was completely and utterly awful. So you get a list of rows, and then you get a list of the values, and you have to go through and iterate the values. Here you can get an individual value, and you can reset it to something different. At the end of this, you've changed the data. We don't have to explicitly return the transaction. But at the end of this, these are working live on the actual class structure of this particular transaction. So any changes you make are right there and then. What can you do in a filter? Anything. Right? You can remove the transaction entirely. Right? I found a transaction, it's for this table, ignore it. Right? I can add data, I can remove data, I can change the format of data, I can merge rows together, I can merge columns together. You name it, you've got full access to that data in its raw format. Anything you want to do is possible within a filter. However, be aware, the more complicated your filter, it is going to slow down the processing. Right? You can't do this for nothing. Yeah. 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 Yeah, that would be a way of doing it, but yeah. We are actually going through a process right now of checking all of our filters, particularly our JavaScript filters, and working out whether they would be more efficiently written in Java. And that's because we were using an old version of the Rhino JavaScript environment, and we realized that actually on one particular filter, P key, in fact, we were wasting 4 microseconds every single time we processed an individual transaction, and it was a memory leak within the Rhino libraries. Updated to the latest version of the Rhino libraries, we saved one of our customers. They had a permanently increasing latency on their system, upgraded to the latest version of the Rhino libraries, and it went away. Now, had we done it native in Java to begin with, possibly it wouldn't have been a problem, but those are the kind of things you do have to be aware of, right? You're changing data, it requires some time to do it. So most of the time our replicator runs will run with 512 meg. If you've got larger data sets, obviously it depends on the size of your transaction, because that transaction ends up being in memory. And the standard setting is actually we keep 10 transactions in memory. So you need enough memory allocated to your replicator to store the equivalent of 10 transactions at the maximum transaction size. 512 meg is our normal. I think we upped it to 1 gig just recently as a standard. Sorry? Yeah, you can change that when you do the install. You can, change the configuration, restart the replicator, and it'll do it. It's all written in Java, so it's a case of increasing the Java heap size each time. So I wanted to talk very, very briefly just about Kafka and what we're doing. I realize I'm running up to time, but if everybody is willing to just give me an extra 5 minutes, I will go over this. So Kafka is really interesting. Kafka, for those that don't know, message bus system, very, very simple method of exchanging data between different systems. Send out a message, you publish a message, and downstream systems subscribe to the message, and then accept that message incoming and say, oh, okay, I'm going to do something on it. So obviously being able to replicate your data out over Kafka opens up a whole range of possibilities. Maybe this is your method of how you get your data into a different database. Maybe this is your method of how you maybe update or configure something to be triggered down the line. Somebody uploads a picture, you send a message out over Kafka and a downstream application says, oh, I see there's a new picture, I'll create new thumbnails for it. And that becomes a way of triggering that process. It's very, very high performance, and I mean super high performance, very, very flexible, very, very practical. However, it's not a database, right? Don't get me wrong. It is a message bus system. It's a message queue. It's not a database. And it also has its limitations. So one of the first things that we got to think about when we go into Kafka, right, is how do we output the information? Do we output it as a CSV row? Do we output it as a JSON, converted JSON of an individual row into a JSON record? What do we do with encoded binary fields? What do we set as the message topic? What do we set as all of those message values as we send it over the system? All of these systems, by the way, I haven't made any decision on them, but I'm just trying to throw them out there so that you can see actually heterogeneous replication is not as simple as it sounds. It is a really, really complicated process. And then we go back to the impedance problem, right? What do I do if I get 1 million transactions and I'm sending it out to Kafka, million row transaction? Do I send out 1 million messages? If I get stopped in the middle of that, do I restart and send another 500,000 messages when I start up again? How do we record where we've actually reached? Right? Do I send a message out on the message bus saying I've got this far so I don't redo it another time? Yeah. Yeah, so the standard size of a Kafka message is 10 meg. Yeah. I'm trying to work out a good way of doing it, and I haven't decided it yet. I think, yes, I'm obviously going to have to do things like chunking. I'm obviously going to have to say, maybe I chunk. Maybe you have the option to have multiple rows in a single message, but only up to a specified size. We need to try and work out exactly how we're going to do this, and I'm thinking about it. My main goal at the moment is probably to make it actually as configurable as possible, and then it becomes your problem and not mine. If I've given you options and you choose the wrong one, that's not my problem. And that sounds like an unkind thing to say, but I think it's a very practical one because I don't know your data. I don't know. We have customers who never ever do more than 1 or 2 rows at a time. We have customers who frequently will do 1 million, 2 million, 3 million transactions at a time, rows in a single transaction rather. So for some of those customers, it's going to be practical to do the chunking. For some of them, they're just never going to need it. So I did want to talk just briefly about some of the things that we already do. This is what we do already. This is a list which actually includes some things that we don't necessarily provide. So, you can write out to SQLite. People have done that. You can write out to RabbitMQ. Smart Sheets have a RabbitMQ applier, so you can apply out to RabbitMQ if that's what you want to do. Obviously, I mentioned MongoDB. We do write up to S3. Obviously, we do that as part of Redshift, but there's nothing to stop you from just not doing the Redshift bit. Just dump all of your change logs up into S3, so you've got a permanent copy of all of your changes of data. That's actually something I might just add into our next version as well, just as a simple way of doing it, right? You just want all of your data up into S3. We can do it that way. All of these things, obviously, sources are always harder to do than targets, because we've got to work out how to extract that data out of the system each time. What are we planning on? I'm not going to say all of these are going to come this year, but certainly we are working on many of them. Cassandra will be out very, very shortly. Kafka and Flume and possibly Elasticsearch will be out in 5.3, which will be September this year. And then, native JDBC into Hadoop. So Hadoop has moved on from when we did our original Hadoop applier. There's now a very, very good JDBC interface. I need to work out whether it's faster or whether it's more efficient for doing that. And we can then do JDBC, whether it's into Impala, HBase, or Hive. Postgres, actually, historically, Tungsten Replicator was written for Postgres first. We moved to MySQL about 8 years ago. So supporting Postgres is something that we actually just need to add back. In fact, if you look at the code base, everything is still in there. We just don't publicize the fact that it's possible. And then in terms of extraction sources, I'm working right now on a REST API input. So if you just wanted to be able to feed the replicator with a REST API call and say, here's a record of data, apply it to my MySQL database, I'd like to do that because it may be a simple way for us to actually then add other sources. We just build something that reads from the database and writes to the REST API. Yep. Sorry, say that again? Yeah. Yeah. Yep. So, that's the thing with the replicator, right? Once we've extracted the THL can be applied anywhere. So if you have multiple downstream replicators, or even multiple services in the same replicator, you're going to end up applying into as many different targets as you've got. Obviously, other things, like I said, MongoDB, Couchbase, CouchDB, we have been asked about these in the past. In fact, I was asked at the show yesterday if we did MongoDB. They have a really, really simple changes feed that we could just sit there and subscribe to. And I would like to do that because I think it's a relatively low-hanging fruit. And where next? Well, please go and download the replicator if you haven't downloaded it already. I am aware of the fact that the Tungsten Replicator on GitHub, we don't have binaries up there, and I'm working on that one right now. I was trying to sort that out. Please also go and have a look at my blog. I admit I don't always post very frequently, but when I do post, it tends to be something juicy. So go to mcb.guru, which is my blog. You'll be able to pick up everything from there. And that's it. Anybody have any questions? Anybody have anything they want to ask beyond what we've already discussed? Nope? Okay, that's great. Thanks, everybody. I'm done.